Up to this point in our system design series, we have focused on the happy path, that is infrastructure, networking, and databases working as expected. But designing systems for perfect conditions is the easy part. Real engineering begins when things start breaking. In production, servers crash, networks slow down, and dependencies fail. The systems that survive aren't lucky, they are designed for failure. In this video, we move beyond basic architecture and explore how to build resilient systems that continue to operate at scale. To understand how we stay online during a crisis, we first have to look at our first line of defense against a total shutdown, and that is fault tolerance. Let's start with the cornerstone of reliability, and that is fault tolerance. At its simplest level, fault tolerance means your system continues to function even when specific parts of it fail. In a distributed environment, failures aren't rare anomalies, they're expected, everyday events. Think about it this way: a service will eventually crash, a network packet will inevitably drop, and a database replica will eventually become unavailable. A truly fault tolerant system is designed so these individual failures don't trigger a total application blackout. For example, if one of your application servers goes offline, a healthy system automatically routes that traffic to a secondary server without the user even knowing. Similarly, if a primary database replica goes down, the system is smart enough to serve those reads from a different replica. The key takeaway here is that fault tolerance isn't actually about preventing failure, that's nearly impossible. It's about handling that failure gracefully so our business stays online. But how do we actually achieve this? The most common and effective way to build a fault tolerant system is through redundancy. Redundancy is a straightforward but powerful concept. It simply means having multiple copies of your critical components. In a high availability environment, you never want a single point of failure. This means running multiple application servers, maintaining multiple database replicas, and even distributing your infrastructure across multiple availability zones. Instead of running your entire application on a single server, you might run it on 10 servers sitting behind a load balancer. If one of these servers crashes, the other 9 continue to operate and the system stays live. This principle of redundancy needs to apply across your entire stack, from your compute and network to your storage and even your regional data centers. Redundancy provides the physical infrastructure that allows our software to be resilient. However, simply having extra servers isn't always enough. Sometimes a failing dependency can drag your whole system down with it, which is why we need a mechanism to cut the power when things go south, and that's where we use a circuit breaker. In a modern microservices architecture, services are constantly talking to one another. Your API gateway might call an auth service, which in turn calls a database, or your main API might need to reach out to a third party payment service. But what happens if one of these downstream services becomes slow or completely unresponsive? If every incoming request keeps waiting for that failing service to reply, your threads will hang, your resources will exhaust, and your entire system can cascade into a total failure. This is where the circuit breaker pattern becomes essential. A circuit breaker acts as a monitor for failures. If a downstream service starts failing repeatedly, the circuit breaker trips and stops sending requests to it temporarily. Instead of making users wait for a long timeout, the system fails fast and returns an immediate error or a cached response. After a cooling off period, the system will allow a few trial requests through to see if the service has recovered or not. This simple mechanism is what prevents a single slow dependency from taking down your entire global infrastructure. Protecting your system from failing services is one thing, but what happens when the failure is actually caused by too much success, like a massive spike in user traffic? To handle that, we need to talk about rate limiting. While circuit breakers handle failing services, rate limiting protects your system from an overwhelming volume of requests. Imagine you have an API designed to safely handle 10,000 requests per second, and suddenly, if you receive a spike of 100,000 requests, your infrastructure could easily collapse under the weight. Rate limiting ensures that clients cannot exceed a predefined threshold. You might set these limits based on requests per second, per user, or per API key. When a client crosses that line, the system rejects the excessive traffic and returns an HTTP 429, that is too many requests error. This is a vital defense against malicious abuse, unexpected traffic spikes, or even just an accidental overload from a buggy script. By enforcing these boundaries, you ensure that a few aggressive users don't degrade the experience for everyone else. Rate limiting is great for rejecting traffic at the door, but what if the bottleneck is happening deep inside your system? And that's when we need to apply backpressure. Backpressure is a concept that is extremely important in high scale systems, particularly when dealing with asynchronous processing. It's a mechanism where a system signals upstream components to slow down because it can't keep up with the current load. To visualize this, imagine a queue based system where producers are sending messages and consumers are processing them. If the producer starts sending messages faster than consumers can process them, your queue will grow indefinitely. Eventually, the system will run out of memory or storage and crash. Backpressure prevents this catastrophe. When system detects an overload, it sends a signal back to the producers to reduce their rate of requests. This feedback loop helps stabilize the system, ensuring it operates within its limits rather than letting it collapse under the mountain of data. You'll see this commonly used in streaming systems, message queues, and reactive architectures. Backpressure keeps our internal pipes from bursting, but sometimes we have to accept that we can't provide the full experience to everyone during a peak. In those cases, we turn into graceful degradation. When parts of a system fail, the goal isn't always to maintain 100% functionality. Instead, we aim for a graceful degradation, where the system continues to operate with reduced features rather than shutting down entirely. Take a video platform for example. If the recommendation service fails, users should still be able to watch their videos. The only difference is that the recommended section might simply disappear or show a generic list. Similarly, if a search suggestion service goes offline, users should still be able to manually type their query and hit enter. The core idea is simple. Your primary functionality should always remain available, while non critical, nice to have features are allowed to fail temporarily. Graceful degradation is a safety net that prevents minor service hiccups from becoming major headline grabbing outages. So, we have learned how to react to failures and manage traffic, but how do we know our system will actually hold up when a real crisis hits? We don't wait for a disaster, we create one ourselves through chaos engineering. Finally, we reach the most proactive tool in our resilience toolkit, chaos engineering. This is the practice of intentionally and systematically breaking your own system to see how it responds. Rather than waiting for a server to fail at 3 a.m. on a holiday, engineers deliberately shut down servers, inject network latency, or kill database nodes during the workday to test the system's behavior. If the system continues to operate correctly despite these attacks, you know it's truly resilient. This approach was famously popularized by companies like Netflix with their tool Chaos Monkey, which randomly terminates instances in production to ensure their software can survive without human intervention. While the idea of breaking your own production environment sounds scary, the philosophy is simple. It is far better to discover and fix your weaknesses during a controlled experiment than to find them during real catastrophic outage. And this brings us to the final key takeaway for this chapter. When systems scale to millions of users, failures are no longer hypothetical situations. They are daily realities. Servers will crash, network will fail, and services will go down. The difference between a system that collapses and the one that survives lies in the design principles we have covered today: fault tolerance, redundancy, circuit breakers, rate limiting, backpressure, graceful degradation, and chaos engineering. These aren't just buzzwords, they are pillars that transform working software into reliable production grade infrastructure. Thank you. I'll see you in the next one.